All right, so today we are picking up with the second half of section 7.2. And so yesterday we talked about this idea of inverse functions, all the kinds of inverse functions we know, and how we were going to learn how to read that table in both directions to look at not just a Laplace transform, but the inverse Laplace transform as well. And I'm going to go ahead and drop the table in the chat, the link for the table. I'll put that in the chat. Again, it will probably be helpful as we go through some of the questions today. Okay. And so if you want to make sure you have that up, maybe off to the side or something like that, so we can refer to it as needed. But yesterday we talked about this idea of linearity, which basically means that we can add or subtract different components and then combine them back together. We can multiply them by a scalar, like a constant multiple, and then just multiply that in afterwards as we move through the arithmetic of Laplace transform, okay? So we spent some time doing some sort of more basic questions, and then we quickly ramped up to situations where we had to use a lot of algebra, in particular, partial fraction decomposition, things like that, to help us move through the question, right? So partial fraction decomposition and clever ways of saying the number 1 were really helpful for us yesterday, all right? And then we finished by taking a look at this particular problem in example 8 right here. And so we did not show the computations for how this partial fraction decomposition gave those constants. But at the end of class, I said that would probably be a good place for you to sort of practice those computations. This would be something that is probably as complicated as you're going to see in this class, right? And so learning what kind of technology, whether it be like a matrix calculator or how we can grind through the systems of equations, all of those would be really useful skills to practice, right? For better or for worse, especially if you feel like you're not good at it, this is the place to really dig in and say, all right, let me see how I can make this better. Okay. And so we did get to a point where we were able to find sort of 4 different functions that we needed to find the inverse Laplace transform of, okay? And so I think that the first 3 specifically, are fairly straightforward in that we can just look on the table and find something. Maybe we need to multiply by a fancy 1, but it's actually not too bad. The meat of our work, however, is really going to be in this last term today. And there's a sort of a new trick that I want to show us about how we might work with that, okay? And so let's maybe make some notes for ourselves right here, just to kind of warm ourselves up. In looking at that table, the link to the table that I put in the chat, can someone tell me what line we might need to use to find the inverse Laplace of 11 over S? You can just leave that. Good, yeah, this one is going to be number 1, right? So this one, you can look at line number 1, we'll pull that 11 out to the front, and then we'll get that 1 over S. And so there's nothing we need to do other than bring that constant out to the front, okay? What about for the second term, this negative 20 over S squared? Which line might we need for that one? Yeah, I would agree. I think we need line number 3, okay? And what about that third term, the 25 over S cubed? Yeah, I think that's also going to be number 3. Okay. Now I will put a note here for these 2 that we probably have to try that idea of a fancy way of saying 1. We might need to do a little bit of algebra work here. And then here's what I'm going to say for this last one. Okay, we are going to try and match this last one to, where did it go? We're going to try and match this last one to somewhere along the lines of line maybe 19 or line 20, somewhere all the way down there. So I'll give you a moment to kind of scroll down to the bottom. So here we're taking a look at maybe number 19, number 20, somewhere down there. That's our end goal, okay? So what I'm going to suggest is we take this last one and we sort of work with it off to the side, okay? And then we'll put it back in line with everything else. And so if we take a look at just this last one, all right, well, let's imagine that we have this 11 s plus 24 all over s squared plus 4s plus 5. All right, so we're going to just look at that one off to the side for a moment. And so before we sort of split fractions here, one thing I notice about the denominator here is that it is very close to being a perfect square. Okay, it's very close to being a perfect square. In other words, if I think about s plus 2, that quantity, and I square it, all right, I end up with s squared plus 4s plus 4, right? So if I take s plus 2 and I square it, I get s squared plus 4s plus 4. And that is so close to the denominator that we have here, s squared plus 4s plus 5, right? So this denominator that we have right here is really just some perfect square plus 1. And so I'm going to actually rewrite it that way, all right? And in particular, I'm going to say that this is 11s plus 24 all over s plus 2 squared plus 1. Okay. Now, this idea of saying this is so close to being a perfect square is something you might remember from way back when. It's a technique called completing. Okay, completing the square. And so we have this s plus 2 squared plus 1 in the denominator, which I think if we're looking at line 19 and 20 in our table, now we can start to see why I would say we're headed towards line number 19 or 20, right? And so what we're going to do is we're going to go ahead and do two things here. We're going to go ahead and take the numerator and we're going to add 0. Okay, we're going to add 0. And just like we had a fancy way of saying 1, we're going to have a fancy way of saying 0. Okay, and so here's how this fancy 0 is going to look. We're going to have 11. And instead of s, I'm going to write s plus 2 minus 2. And then I have that plus 24 at the end. Okay. So just like sometimes we want to say times 1, so we don't change anything, but we make it into a form we want. Today we are saying plus 0. Plus 0 doesn't change anything, but check out what this is going to do for us, okay? So I added 0, which means I didn't change anything. But let me distribute some of this. I'm going to keep that part, but minus 11 times 2 plus 24. Okay, so all I did was I took the 11 times that negative 2, and I sort of brought it out. All right, so I distributed that part. I know normally with distribution, we distribute everything, but keep in mind sort of as you move higher and higher in math, that that's really, you want to be more clever about it. What's going to actually help you move forward in the problem? That's what you should probably quote unquote simplify, okay? And here's why this is so helpful. Now I have 11 s plus 2, and I'm going to combine these last two numbers. So negative 22 plus 24 gives me a plus 2. And now I can split this into two fractions. I'm going to take this 11 times s plus 2 over this denominator. That's going to be my first fraction. My second fraction is going to be 2 over this. All right, so I'm splitting those fractions. Now, bring your eyeballs back to line number 19, okay? In line number 19, in order for us to use that line, right? In order for us to use that line, we want, we want whatever this b squared term to be, we want b on the top. So I know I have a 2 out here, but keep in mind I can pull that constant out to the front. So that numerator is really 2 times 1. This 1 is the b squared, but the 1 that is up here is just the b. Okay, so now I've matched all of this to be line number 19. And again, if we sort of ignore that 11, do a quick visual check. Does this circled expression match line number 20? Right. What is our a value if we want to use line number 20? Good. Yeah, it's not going to be positive 2. It's going to be negative 2. Okay. And so if we now take this part and we put it back into our inverse Laplace, right? We're now going to have a line with 5 different items, 5 different items that we are going to take each one and find the inverse Laplace of each one. Okay. Let's see, how much space do I have left? Okay. All right. So let's be patient. Let's write this all out, leave ourselves some space. We have that 1/5 in the front, the inverse Laplace of 11 over s minus 20 over s squared plus 25 over s cubed minus, right, here's that rest of it, 11 s plus 2 over s plus 2 squared plus 1, and then minus 2 over s plus 2 squared plus 1. Okay. Now I just want to pause for a moment and make sure we understand why the second one is a minus sign, right? Because over here we had a plus sign. But one thing that we need to recall is that originally it was minus whatever we found here, right? So that negative sign gets distributed to the first term that we found as well as that second term. That's a really tricky place that it could be easy to change a sign by accident, all right? So you wanna still have all of those parentheses as needed in your brain when you move through the process, okay? All right, let's close this off with a squiggly bracket. And now we're gonna find the inverse Laplace of each term, okay? So we're gonna keep that 1/5 all the way out in the front, and let's see what we get. So the inverse of 11 over S is just gonna be 11 times 1, right? When I read from the right-hand column back to the left-hand column, it becomes 1 over S becomes 1. Okay. What do you think that second one is gonna be? Take a moment and see if you can think about what that second one will be. 20 over S squared. So when you think you have it for that negative 20 over S, you can type that into the chat. What do you think that's going to turn into when you do the inverse Laplace, when you go from the right-hand column to the left-hand column? All right. Let's see, maybe we do a little bit of side work for this one as well. I think this is a little bit harder to sort of imagine, but we have 20, the inverse Laplace of 1 over S 1 plus 1, right? That sort of fits what we want in line 3. And so if my n value is 1, then I want n factorial on the top, right? So as soon as I pull out that 20, I actually have exactly something that matches the table. So really this becomes 20 times t to the power of n. What's my n value? N is 1. Okay, so this right here on our table, n equals 1. Right? And so we end up with a negative, 20t. Right? So I just want to pause for a moment, make sure that we understand where that came from, right? This is definitely a part in the curriculum where if you have a question, so important to ask, because a lot of silence on my end is like, I don't really know. I can't see all your faces. I can't pick up on body language, all those things that I could in the classroom, right? So if you're not sure where this came from, this is a great time to ask. You can just sort of whisper it to me by sending me a direct message. You do not have to type it out in front of everyone, okay? But I would say as we're using these tables, the most important thing is identifying the piece that you need, right? So this is 1 factorial. That's how we're going to plug that back in over there. Great. All right. Now let's take a moment, all right? It would be especially important for us to see if we can now do the next one, because it sort of follows the same pattern that we just wrote down, except the numbers are a little bit different, okay? So take a moment, see if you can figure out what the inverse Laplace of 25 over S squared is, okay? All right, let's see. So I would have 25 the inverse Laplace of 1 over s to the 2 plus 1. All right, so in this case, it would be important to identify n equals 2. Right? And if n equals 2, that means my numerator better be a 2. And so if I multiply by my fancy way of saying 1, I would have 25, the inverse Laplace of 2 over 2 times 1 over s to the 2 plus 1. And the top 2 is going to go in here to make it 2 factorial, but the bottom 2 is going to come out and be that denominator. And so I believe David is correct when he has 25 over 2 and then t to the power of n, or t squared. Okay. So we'll end up with plus 25 over 2 t squared. Yay, nice job, nice job. All right. Let's figure out these last two. All right, now that we did all the algebra to help us figure out what each of those are, I think that these last two might actually be just as straightforward as the first one, this 11 over f that we took the Laplace transform of, okay? Or the inverse one. And so this first one right here, the s plus 2 over s squared plus s plus 2 squared plus 1, that corresponds to line number 20, right? So we're going to scroll back down in that table. We're going to take a look at line number 20. That's what this looks the most similar to. And over here, the fifth one is most similar to line number 19. And so we should end up with the fourth one being minus 11 e to the negative 2t cosine of t, right? So we have our a as 2, our b as 1, and then our last term here should be minus 2 e to the negative 2t sine of t. That, my friends, is the inverse Laplace transform of our original function in terms of s. Okay. All right. So that finishes up our lesson from yesterday. Are there any questions about this before we take a look at the next section? Or the rest of 7.2 rather? All right, well then, let's move on to the next section. All right, so this second part of 7.2 is called transforms of derivatives. All right, transforms of derivatives. And when we're looking at transforms of derivatives, there's a few things that we want to be thoughtful about, okay? It would be really important to us that the function we're looking at, as well as all of its derivatives, are continuous, right? That means we can think about polynomials. We can think about e to the power of something. Any sort of continuous function we know is going to fall in this category, okay? So continuity is definitely really important. We don't want any points where there's no derivative because that might make things very messy in the system that we're looking at. All right. And I want to introduce sort of a new term here where the nth derivative, so the last derivative we're looking for, is something called piecewise continuous. All right. it's sort of a weird thing to think about, but when we think about continuous in general, we're thinking, okay, whatever the function is, it's continuous everywhere, right? We can take a derivative everywhere we want. But when we say something like piecewise continuous, what we mean is like, maybe we have a place where it's continuous, and then it sort of jumps a little bit, but the next piece is also continuous. And then the next piece is also continuous. But there are moments where that derivative is not continuous, all right? But those are sort of like very small moments in time. And when we're thinking about making sure that it is piecewise continuous, all right? So if we have all of these derivatives are continuous, and then the one that we're interested in is piecewise continuous, then we can actually say the following, okay? We can say that if we have a Laplace transform of the nth derivative, okay? So f to the n is really saying the nth derivative. Right. And there's sort of this long fancy formula that follows, but really this is going to be circling back to a wonderful question that was asked a couple of days ago, which is, why do we need to use Laplace transform? Okay, like what good are they? What do they do for us? And what they do is they help us solve differential equations. Okay, so this is sort of adding to our technique. We've learned so many techniques. We just finished looking at the series solution technique, right? And now we're going to take a look at a technique that uses Laplace transforms, right? So we have this nth derivative, and I actually want to be a little bit more accurate. I'm going to say that this is the nth derivative of some function with respect to t, right? And it turns out that that derivative, or the Laplace of that derivative, is going to be s to the power of n times f of s, uppercase f of s, minus s to the lose a power n minus 1 times the original functions at 0, okay, minus s to the n minus 2 f prime of 0. And like a lot of things, it sort of keeps going until we get to where we want to stop, which is s. And we're going to have that times our f of n minus 2. So whatever that second to last derivative is. And we're going to plug in 0. And then the last one is f to the almost at the end derivative evaluated at 0. Okay. Now, for our purposes, right, this is a very, very long formula, and the higher the degree, the more terms we have. But in our class, we're really focused on finding first order differential equations and second order differential equations. And so we don't need that many terms, but I'll write down what is going to be important for us. Okay. For our purposes, we're going to be focused on the following 3, okay? We're going to say that the Laplace transform of some function is going to be capital Y of s. Okay, so Y being whatever function that might be. It could be like Y is like an f. Okay, this is going to be our solution form. our first derivative, so the Laplace of the first derivative, we're going to use just the last two terms here. Okay, just the last two terms. We're going to say that is s y of s minus y of 0. Okay. If we want to find the Laplace transform of the second derivative, we're going to keep some of the terms, but not all of them. Okay, so we want to think back to up here, which ones do we need? Well, if our n is 2, we're going to have s squared y of s. And then we're going to sort of keep going until we get to almost the end. Okay. So that will give us s squared capital y of s, uppercase y of s, minus s lowercase y of s, or y of 0, excuse me, minus y prime of 0. And the way that I've structured this, we've got a y prime, a y double prime. That's a pattern we've seen a lot from like literally almost day one, where we said, let's find our solution form. Let's take that derivative. Let's take the second derivative. Then we just plug it all back into the differential equation, and we're going to be able to find a solution. Okay. And so that theme hasn't changed. We're just doing it with different structures. We did it with series. We did it just with regular functions. But now we're doing it with the Laplace transform. Okay. All right. So knowing all of that, let's go ahead and try doing a problem. All right. Let's see what this actually looks like. So I think a lot of times it's easy to get bogged down in something like that and say, how am I supposed to even do that? I don't know what all those letters mean. But sometimes when we do it in practice and then we sort of circle back to our expression, it actually makes a little bit more sense. Okay. All right. So this is where I am going to need some of your help. All right, we're going to go through this particular question in 3 different ways. And some of these ways are going to be easier than others. Some of them are going to be more time consuming than others. But regardless, all 3 methods should get us to the same answer. Okay. So let's take a look at this second order differential equation. All right. So method number 1. Let's go ahead and use our characteristic equation, our associated characteristic equation, to find the left-hand side of things. Right. So use that characteristic equation to find y sub c. All right, so our characteristic equation in this case will be m squared minus 10m plus 9 equals 0. We know that factors into m minus 9 and m minus 1. And we know that that gives us roots of m equals 1 and 9. Okay. What does that give us for the general form of our y sub c? All right, go back into your notes, reach into the crevices of your brain from several weeks ago. What form is that?
Is it the C1 e to the x1 plus C2 e to the x2?
Yeah, and by X, I think you mean the M,
R,
right?
yeah,
Yeah,
the M.
exactly. Good. All right, so we'll have C1 e to the t, right? 1t, because 1 for the 1, plus C2 e to the 9t. All right, and we'll put a box around it, not because this is a final answer, but just to kind of save that in our brain. We're going to need that to come back to, okay? All right, so characteristic equation to find y sub c. That's generally the most straightforward way if you have constant coefficients, right? If we have functions in there instead, that's a different game, right? Then we're looking at the non-constant coefficient techniques. All right, let's divide this. Name one method for finding the solution now, knowing that we have a non-homogeneous differential equation, right? The right-hand side is not 0. The right-hand side is 5t. Again, you might have to flip back through your notes. Okay, so let's try that one first. There is another way we can do this. Anybody think of that other way we can do that? Exactly. So we're going to do this once with superposition. We're going to do it again with Wronskian. So if those were methods that like didn't really stick the first time, sometimes just seeing it again and realizing in the bigger picture how they all fit together is actually a little bit helpful for like making things stickier. Okay, so we're going to use superposition to find y sub p. And so our guess here, we're going to have y sub p. Let's see, we have a 5t over here. And so a good guess might be at plus b, right? Something of a linear form. Now, I should always double check with my characteristic equation. Are there any duplicates here that I need to be concerned about? No, there's no duplicates, right? Excuse me, these are exponential and this is linear. So nothing is going to be double counted. We don't need to multiply by t here, okay? And actually, I think the superposition one should work out fairly nicely for us. Our yp prime is just going to be a, and our yp double prime is going to be 0. And we're going to take these and we're going to plug them into our differential equation, right? So we have y double prime minus 10y prime plus 9y equals 5t. And so everywhere I see the double prime, I'm going to put that 0. Everywhere I see the single prime, I'm going to put a. Everywhere I see the y, I'm going to put at plus b. And so we're going to end up with 0 minus 10a plus 9at plus 9b equals 5t. Right. This one I think is not too bad to solve by hand, all right? I see that there's a 9at on this side and a 5t on this side. That means I can solve for a. And in particular, 9a equals 5, so a equals 5/9. Right. All right, we can use that to find b, right? Because there's a second equation here. The second equation is negative 10a plus 9b equals 0, because none of those terms have a t in them. So if I plug in my a of 5/9, I'll get negative 50 over 9 plus 9b equals 0. I'll do some computations and I'll end up with b equals 50 over 81. Okay. You should confirm these numbers on your own time, right? Making sure you know how to go through that process and like how you're going to be able to get to that number. right? Again, there's systems of equations. You could set up a matrix, lots of options here. But now that we have these two, our y sub c and our y sub p, we can find y equals the linear combination of those two solutions, right? So we end up with y equals c sub 1 e to the t plus c sub 2 e to the 9t, that's my y sub c, plus 5/9 t plus my b, which is 50 over 81. Right, so the first part of this comes from our y sub c, whereas the second part comes from our y sub p. Now, I just want to make this part really clear. I've seen not a lot of you, but some of you who find this part and then plug it in, but you don't find the coefficients. If you don't find your A and B or however many letters are there, you can't plug it into your general solution form. Okay, so you have to find those coefficients before you move on. Now, let's go back and look at the question, because my question to you is, are we done here? And if we are, how do we know? And if we're not, how do we know? Exactly, right? If all I gave you was the first part, y double prime minus 10y prime plus 9y equals 5t. If that's all I gave you, then you would be done. All right. But this is a message that some of you need to hear. If you have the initial conditions, you have to find a number for C1 and C2. Okay. If you have those initial conditions, you have to finish off and find a number for C1 and C2. So the only unknowns you have are T. All right. And T will change depending on whatever time you happen to be looking at. All right. And so maybe we can write this as a separate step 4, use the initial conditions to find C1 and C2. Okay. And so our initial conditions usually require us to take a first derivative, right? If we have 2 of them, we have to find a first derivative so we can plug in both of those. Let's go ahead and use our first initial condition first. That's y of 0 equals -1. That one I can plug right in, right? Y of 0 equals -1. And so everywhere I see a t, I'm going to put a 0. And I'm going to find that e to the 0 goes to 1. 5/9 times 0 goes to 0. And so when I clean that up, I end up with -1 equals c sub 1 plus c sub 2 plus 50 over 81. But I'm going to go ahead and subtract that 50 over 81 to the other side. And I'm going to end up with -131 over 81 equals C1 plus C2. Right. And now sometimes we get lucky. Sometimes we plug in that first differential or first initial condition and out pops one of the constants, right? This is not one of those cases. It is a situation where we're going to need to apply in the other equation so that we can find our C1 and C2. Okay. And so to do that, we're going to need to find our y prime. All right, our y prime of what we had for our y. Our y prime in this case, we have C1 e to the t plus 9 C2 e to the 9t plus 5/9. Right? t goes to 1, the 50 over 81 goes to 0. My second initial condition says y prime of 0 equals 2. So 2 equals, let me plug in a 0 everywhere I see a t. And we'll end up with 2. I'm going to subtract this 5/9 to the other side. 2 minus 5/9 gives me 13 over 9 equals C1 plus 9 C2. Now I've got one equation here. I've got another equation here. And all I'm going to do is I'm going to solve this one by hand, but you could also put this into a matrix. I'm going to take this equation and I'm going to subtract it from that equation. Okay, that's going to cancel out my C1s. So if I subtract this, I'll get 131 over 81, which equals negative C1 minus C2. I'm going to combine them. 248 over 81 equals, the C1s go away, equals 8C2, and C sub 2 equals 31 over 81. All right. I know I'm moving pretty quickly through the arithmetic. Again, you can do this on a matrix if you want. You don't have to do these by hand. But thinking about the flow of these I want us to focus more on like what we need to find and how we find them, and, you know, save sort of this arithmetic work for like the privacy of our own learning environment. Okay. But once we find C2, we can use that to find C1 in a number of ways. I chose to plug C2 back in here and find C1. And so that gave me a C1 value of negative 162 over 81. Okay. Now again, if we get to this point and you don't write anything else, I cannot give you full credit. You have to come back. You have to write out your answer with your C1, your C2, your A, your B, all as numbers. Okay. I cannot stress that enough. We end up with a final answer of C1, which is our negative 162 over 81 e to the t. Our C2, 31 over 81 e to the 9t. All right, so all of that came from that y sub c plus 5/9 t plus 50 over 81. Okay. That, my friends, is your solution. Yeah, so some people, you can certainly take that negative 162 over 81 and turn that into a negative 2. Sometimes people like to take like a common denominator, bring it out to the front so that on the inside they have all whole numbers. And so that might be one reason why someone would keep that as a denominator of 81, right? And so what I mean by that is some people might write something like this. Y equals 1 over 81, bring that out to the front. Negative 162 e to the t plus 31 e to the 9t plus 45t plus 50. That might be another way that folks write that. Yeah, that's the only reason that I would say, like, if you happen to have all the denominators the same, you could go ahead and bump it out to the front, but you don't have to, right? You could certainly change that leading coefficient to a negative 2 and it would be absolutely fine. Yeah. All right, so let me get this all on one screen for you. This was meant to be a review, right? I know your exam next week is not cumulative, but as we move forward and we learn different techniques, I want us to just remember, like, we knew how to solve these problems before. We had other techniques. What were those other techniques? Because if you do move forward in differential equations, being able to choose the most efficient one is a skill that you certainly want to have. Okay, so here's one variation where we used the method of superposition to solve this problem. Okay. Now, as David pointed out earlier, we could also solve this using the Wronskian. Okay, and someone asked yesterday about tabular integration, and so we're actually going to be able to highlight that method here as well. Okay, so I think for the sake of time, how do we want to do this? Let's see how far we get. Okay, so method number 2, we are looking at using the Wronskian for the y sub p part, okay? And so method 1, or starting with finding our y sub c, I'm gonna grab the y sub c from above because that part is the same. It's still a constant coefficient. So we're still gonna use that characteristic equation. And so from above, y sub c equals c1 e to the t plus c2 e to the 9t. Okay. Now this is important for our Wronskian setup because in order to use the Wronskian, we need a y sub 1 and a y sub 2, right? That helps us find our Wronskian and then plug it into that big old equation, right? So let me actually, okay. All right, so from y sub c, we have our y1 and our y2. This is where that Wronskian comes into play, right? And so we want to think about that Wronskian is our y1, our y2. Then we take the derivative of each one for that second line, e to the t, 9e to the 9t equals, we're going to take the ones along the main diagonal and multiply them. And then we're going to subtract the ones along the non-main diagonal. So 9e to the 10t minus e to the 10t is going to give us 8e to the 10t. Right. Now, most of us are doing pretty well with all of those like really common algebra rules, like what do we do with those exponents? But this is a good place, no matter how confident you feel in your work, this is a good place to just pause and double check because you're going to use your output here in the rest of the problem, right? So if this step is wrong, everything that comes after it is going to be wrong. So as you find those important junctures, it would be, I think, really good mathematical practice to say, let me pause here. Let me make sure I did this part right, because I know it will impact the rest of the problem. All right. Oops. All right. We're going to plug this into our big old formula that we have. Negative y1, the integral of y2 g of t over the Wronskian, plus y2, the integral of y1 times g of t over the Wronskian. All right, so I get negative e to the t, the integral of e to the 9t times my g of t was 5t. That's like the term on the other side. Over my Wronskian, which is 8e to the 10t dt. Plus e to the 9t, the integral of e to the t times 5t over 8e to the 10t dt. All right, let's be really careful about our simplification here, all right? In the first term, I'm going to bring the 5 and the 8 out to the front. And so I have negative 5 over 8 e to the t. And let's see what else stays or goes away. So my e to the 9t and e to the 10t, there's going to still be an e to the negative t, right? And so I have t e to the negative t. Plus, I'm going to go ahead and bring that 5/8 again out to the front. So 5/8 e to the 9t. And let's see what cancels out over here. I end up with t times e to the negative 9t. All right. Now, to integrate both of these, we can use tabular integration, okay? So I saw some people doing this, like things that look like this, using regular integration by parts, and that's absolutely fine, okay? Yesterday, I did say that we can use tabular integration, a sort of shortcut to integration by parts, as long as u equals a polynomial. Okay, that's the part we really need to say to ourselves in our brain. Tabular integration is a shortcut. It's a shortcut for integration by parts as long as your u is a polynomial, right? Because the table has to end at some point. And polynomials, as we take those integrals or derivatives, they get to 0, okay? So let's do that tabular integration off to the side. I'm going to go ahead and do this one in blue. So if I were to set up tabular integration for this, I'd have my u and my dv column. My u is t. I'm going to take that derivative, so t, 1, and 0. And then my dv is my e to the negative t. I got to take that integral as I go down. Negative e to the negative t, e to the negative t. And the way tabular integration works is then you go across those diagonals, right? Like that, 1 times e to the negative t. You're going to keep the sign of the first one. You're going to change the sign of the second one. And you sort of keep alternating depending on how many rows you have. You keep the sign, you change the sign. You keep the sign, you change the sign. Okay. If we set up one for the second integral, u dv, again, our polynomial has to be our u. So t, 1, and 0. And on the other side, we start off with our dv and we integrate. So we get negative 1/9 e to the negative 9t. And then we get 1 over 81 e to the negative 9t. And just like the other table, we're going to multiply sort of along those diagonals. We're going to keep the sign of the first one. We're going to change the sign of the second one. And we're going to keep going however many rows we have there. Okay. But if we plug these all in, that means that the thing in the blue becomes, let's see, this would be negative t e to the negative t minus e to the negative t, because I have to change that sign. All right, so negative t e to the negative t minus e to the negative t. Plus the second one is going to be from the purple table. We're going to keep that first sign, so negative 1/9 t e to the negative 9t. We're going to change the sign of the second one, so negative 1/81 e to the negative 9t. All right. So if you're a fan of tabular integration, I quite like it because especially if I have t to a higher power, it makes it go much more quickly. And as long as I remember to keep change, I'm not going to lose sight of the signs. All right. All right. Now we need to go through and simplify this. Okay. And so if we simplify this, we end up with, let's see, 5/8. So I'm going to distribute and distribute. So 5/8 t e to what power? When I combine those two e's to some power, what's the ultimate power at the end when I simplify? Yeah, it's going to be 0, right? And so this is something I just want to point out because sometimes when we do this part incorrectly, it makes everything else much more complicated. T plus negative t is 0. So I really have e to the 0 or 1 here, okay? So I'm going to keep going and keep distributing. I'll get plus 5/8 for the same reason. And then I get -5/72t, and then -5/648. And if I combine my like terms here, I'm going to end up with 5/9 t. Oh, shoot, we saw that before, plus 50/81. And this, my friends, this was our A from the superposition. This was our B from the superposition, right? So it's a pick your poison kind of situation, right? Which way do you feel more comfortable algebraically? Play to your strengths, right? All right, let's put those together. We find our y. We get y equals C1 e to the t plus C2 e to the 9t plus whatever I just found here. 5/9 t plus 50/81. It's the same problem as before. So find C1 and C2, and then everything else is like above. Okay. So if we get this all on one screen here, the only part that we did differently was finding that particular solution, the y sub p. Okay. Other than that, the first step, the third step, the fourth step, all of those other steps are the same. All right. But we have one more method, right? We have one more method, which is the Laplace transform, okay? Now, again, some of these methods are faster or slower right now, depending on the context of the question. But as you move forward, sometimes you'll be forced to use one versus another, okay? And so I know that there were a lot of folks in the chat about, or on the discussion about the series solutions, like why would we ever use a series solution because it's so much longer? It will be a structure you need at some point if you're looking at Fourier transforms or Fourier series. Okay, so there are other things to come that will require different techniques. And so this class is really like, it's like a sampler of all of these different techniques. Okay. All right, so let's take a look at this very last method. All right, we're going to do the same problem, but in a third way. And this third way is going to be using Laplace transform. Okay. And so here's where our steps start to look a little bit different. Okay. Our first step will be to transform our differential equation into something with an S in it. Okay. And so our differential equation looked like this: y double prime minus 10y prime plus 9y equals 5t. And we're going to transform every single one of these terms. The things on the left-hand side, all right, earlier, before a little review of these two methods, earlier we talked about how we write these three, y double prime, y prime, and y with the Laplace. Using our table, we can write the right-hand side. And so here's what we get. S squared y of s minus sy of 0 minus y prime of 0. Let's do some color coding here. I think that will be beneficial. Y double prime all gets replaced by this y double prime. Okay. Minus 10 times whatever we had for y prime, which was s, capital Y of s, minus y of 0. Plus 9 and y was just y of s. Equals 5 times the Laplace transform of t. Let me pause here for a moment. I'd like you to go back to that table and tell me what I can write instead of t once I apply the Laplace transform. So let's keep in mind here, we're looking at the left-hand column now, right? I have a t. I want to go in the direction where I end up with an s. I have a t. I want to go in the direction of s. Which line should we use? Maybe we start there. Which line in our table should we use? Yeah, we're going to use line number 3. And if we're going to use line number 3, well, then we need to know what value n is, right? So according to this, what is our n value? Good, n is 1, okay? And so we just need to plug it into the formula n factorial over s to the n plus 1. Right? Everywhere we see an n, we're going to replace that with 1. And so that should give us 5 times 1 over s to the 1 plus 1. And we can write that as 5 over s squared. Okay. So that table, all fantastic, right? Someone sat and did all of those formal definitions for you, so you don't have to do that and you can use the table, but it's so, so important that we know how to read the table. Okay, and so if that's something you're feeling a little insecure about, I would definitely encourage you to take some time today and tomorrow and this weekend to make sure you feel really good about going and using the table. Okay. Like so many things to come, if you're an engineer or computer science or mathematician, if you don't know how to use your tools, it almost doesn't matter, right? Okay, so we've made all of our substitutions. Here's what we're gonna do next. We're gonna go ahead and we're going to, let's simplify this first. And after we simplify, we're actually gonna plug our initial conditions in, okay? So when I say simplify, here's what I mean. We have s squared y of s minus s y of 0 minus y prime of 0 minus 10 sy of s plus 10 y of 0 plus 9 capital Y of s equals 5 over s squared. And I want to see if I can combine some like terms before I do anything else, all right? And so I notice that I have s squared y of s minus 10 sy of s plus 9 y of s. So I'm sort of gathering these in the front because they all have a y of s. In other words, this term, and this term all have that y of s. And now let's see what else we can sort of combine. I have my y prime. That one doesn't combine with anything, and that's okay. I have my sy of 0 and a 10y of 0. Those don't combine either, but that's okay. So I'll just write them out. All right, now we're gonna take our second step. And we're gonna go ahead and plug in the initial conditions and isolate y of s. All right. So what are my initial conditions? We said that y of 0 is -1 and y prime of 0 equals 2. And so if we sort of think about where we're going to plug things in, y of 0, I'm going to replace with -1. And y prime of 0, I'm going to replace with 2. Does that make sense? So all the yellow and blue part, I'm going to replace with either -1 or 2. This is going to give me y of s. So I'm going to take out this, I'm going to take out this factor, y of s, and I'm going to leave everything else on the inside. S squared minus 10s plus 9 oh shoot, that kind of looks like a characteristic equation. Minus s times -1 will give me plus s minus 2 minus 10 equals 5 over s squared. All right, so we plugged in our initial conditions, we isolated our y. Now, or we plugged in our initial conditions, now we need to get this capital Y of s by itself. So I'm going to take these terms, whoops, I'm going to take these terms, I'm going to move them to the other side, and then I'm going to divide by this s squared minus 10s plus 9. So I get y of s squared minus 10s plus 9 equals, let's see, when I add these to the other side, I have 5 over s squared minus s plus 12. Okay. But I'm going to go ahead and put these all over. No, I'm not going to do that. All right, now I'm going to divide by this quadratic-y looking thing in the brackets. Y of s equals 5 over s squared times s squared minus 10s plus 9. So I'm dividing the first term by that quadratic, and then minus our s minus 12 over that quadratic-y situation. Now we have an expression that has a bunch of s's in it. But I want my answer to have t's. Here's where we go back to the table. And now we're looking at the right-hand column, and we go back to the left-hand column. Okay, so all this practicing of how we use the table in both directions, this is why we need this. Okay, to start our problem, we read the table in one direction. We change this all to be in s's. That is, we apply the Laplace transform. We plug in our initial conditions, we get an answer in terms of s, right? You'll notice we didn't do any calculus here. We have a solution, but the solution is with the wrong letter. We need to put it back with the right letter. And so this is where we're going to use in our step 3. We are going to apply the inverse Laplace transform of y of s to get our solution y of t. Now I'm going to set this up for us. And sort of like yesterday, I'm going to ask you to work through this. Come back tomorrow ready to contribute to a conversation where we talk about how we move through this problem. Okay. So our Laplace transform here. If I want to find the inverse Laplace of 5 over s squared minus 10s plus 9, minus s minus 12 over s squared plus minus 10s plus 9. What are some ideas we have? How can we start? How can we even start here? This is like a lot, right? This is the most complicated one that we've seen in terms of a Laplace transform. Yeah, we could factor the denominators, then a partial fraction decomposition, okay? And I'll say, let's do one better. Let's take these two, let's turn it into a single fraction. and then let's do partial fraction decomposition. Okay. And so here's what I mean by that. We're going to do the inverse Laplace. If we want to combine these into a single fraction, all we need to do is take that second fraction and multiply by s squared to get the denominators to be the same. And when we do that, we'll end up with 5 minus s cubed plus 12s squared over, and I'm going to go ahead and factor this for us, s squared s minus 9 s minus 1. Okay, but your instinct is exactly right. We're going to use partial fraction decomposition here. Okay, and just to make sure that we are setting this up correctly, and then I'm going to leave you to do the rest. How many partial fractions should we have based on the denominator? We're going to have 4. Good, good, good. All right, tell me what the denominator of the first fraction is going to be. What about the denominator for the second fraction? Good, good. Okay, so that was part of the discussion we had yesterday. When we have a linear factor and it's repeated, we need to account for both versions of it, or however many repetitions we have, okay? Plus, the third one will be s minus 9, plus the last one will be s minus 1, all right? But what about these numerators? Are they going to be constants? Are they going to be linear? Are they going to be quadratic? What form are these are the coefficients at the top going to be? Yeah, they're going to be constants. A, B, C, and D. All of these are linear. I know s squared is quadratic, but the catchphrase is irreducible quadratic. That's reducible, so I just keep it as a constant on the top, okay? And so it is 11. I want to respect your time here. Please come back tomorrow with the coefficients, A, B, C, and D. All right, you already know what the answer is. We found our answers using 2 other methods. Now we just have to confirm it using this third method. Okay, so I will see you folks back here tomorrow. We will come back, we will finish this problem, but you are gonna help me finish this problem. All right, so don't not do it and then walk in and be like, I'm ready to listen. Like, I want us to engage in this process, okay? So I will see you folks tomorrow. Have a great rest of your day. And let's come in ready to work on this tomorrow.